Okay, that's good. So thanks very much for the organizers to having me today here. I'm very pleased to talk about my research on operando of generation of nanomaterials. But firstly, I would like to say that I have been involved in several supergene projects since my PhD, and this hydrogen fuel cell supergene research hub is a great platform for me to meet people from different backgrounds and to learn different perspectives. And I think this is very important for early career researchers such as me. So just for my research, I have been working on advanced materials and material processing for solid oxide cells, especially the perovskite type oxide. So these materials generally have lower activity compared to the nickel-based thermal electrodes, although they have a very promising properties as well. So strategies to promote the activities of this material has been developed. In the past, I have been working on using impregnation technique to improve the properties of the perovskite oxide. And indeed, we have a very much improved performance of this material, also almost comparable to the nickel-based thermate. However, the problem with this method is that the nanoparticles tend to grow together, leading to inevitable performance degradation in long-term operation. And at the moment, I'm working on using exhalation as a technique to address the problems with associated with the problem to address the problems with nanoparticle growth. So I think Dragoš has just give a very nice talk on the exhalation materials. So probably I don't need to speak a lot more about the background. So just to stress that exhalation through the electrochemical reduction, in another word, electrochemical switching is much more efficient, and it is well suited to electrolysis operation. Therefore, it can be used as a vehicle for operando generation of nanomaterials. So far, there are very limited reports on this. So the aims of my project is to explore the exhalation materials in solid oxide cells, specifically to investigate operando generation of nanomaterials in CO2 electrolysis conditions, and also to understand the material properties linking to their performance, as well as to understand the mechanisms for electrolysis, for exhalation using different techniques, including the in situ techniques. A little bit of fundamentals for CO2 electrolysis here, just in case this is not familiar to many researchers. The methodology we used was to apply the interesting exhalation materials such as this as a fuel electrode in SOEC, and to apply a potential across the material in pure CO2 atmosphere to generate nanomaterials without any pre-reduction in hydrogen. Here I'll show you some results we've got on this material and the nickel and iron co-doped lanthanum calcium titanate. We prepared the cell in the configuration illustrated here. After preparing the cell, we heat it to 900 degrees C and then switch on CO2 gas to the material and applied a varying potential to the cell to trigger the generation of nanocatalysts. Here are the initial results from switching. On the left, we have the resulting current density during switching at different potentials. And on the right, we have the CO2 electrolysis performance, the impedance results of CO2 electrolysis at different after switching at different conditions. So we can see that after switching at 2.2 volt, the resulting current density shoot up to a very high value, whereas at lower potential, the current density values are very low and cannot sustain during the switching time. And after switching at 2.2 volt, we have greatly improved cell performance for CO2 electrolysis. this is really due to the introduced nanocatalyst. So this shows how the potential affect the extrusion behavior. We also look at the impact of temperature. So here, after switching at 900 degrees C, we lower the cell temperature to 850 and 800 degrees C, and then we did the switching at these at 2.2 volts at these temperatures respectively. We monitor the CO2 electrolysis performance after switching at these temperatures, and we also test the fuel cell performance in pure hydrogen after each switching. We can see that further switching at 850 degrees C has resulted in further improvement in the cell performance. And in fact, after switching at 850 degrees C, we have a even higher performance at this temperature than after switching at 900 degrees C. And then the fuel cell performance showed a maximum power output at 850, reaching almost 950 milliwatt per centimeter square. So this shows that the temperature can be an interesting parameter to further improve the extrusion phenomenon. So it can be used as a controller to optimize extrusion as well as cell performance. So about the microstructure, here we look at the fuel electrode microstructure after testing. Indeed, we see various nanoparticles decorating on the surface of the perovskite. When we look at the microstructure carefully, we can see that across the thickness of the electrode, there are different nanoparticle size distribution. In the inner electrode area, there are more bigger nanoparticles, around 90 nanometers, whereas the nanoparticles at the outer electrode area are primarily around 30 to 40 nanometers. So this is very interesting, but it's probably more interesting to look at to directly linking the nanoparticle parameters with the switching condition. So that is what we are trying to do at the moment. We also look at the impact of fuel composition. So just briefly, we saw that when we do the CO2 electrolysis in pure CO2 gas at high voltage, we have a limitation probably from slow diffusion or surface reaction for CO2 reaction. And this has really limited the performance. And by just introducing a small amount of hydrogen into the CO2 gas, that has been significantly improved. So that just showed that there are some interesting material properties that linking to the surface reaction for CO2. So that probably also affected the extrusion behavior. So we're trying to understand more of this contributing material property so that we can optimize the extrusion and then promote the cell performance further. We also look at another composition, in this case, the lanthanum cerium nickel titanate. It is a very interesting material as here we have a much higher doping level at the B side. So that means more nanoparticles will be produced. And also in literature, this composition has been reported to have a extrusion of cerium and nickel simultaneously. So that will probably bring very interesting functionalities. So we first look at the reduction behavior. Sorry, I lose the control. Can you move to the next slide, please? Okay, it's working now. Thanks. So we firstly look at the reduction of the material. To our surprise, we don't see the emergence of cerium apart from nickel. And alternatively, okay, I think my Wi-Fi is becoming quite slow here. And so alternatively, when we anneal the material at different temperatures in air, we can see now the growth of cerium cube on the surface and the extent of cerium growth as well as morphology of these cereal hills vary differently and at different temperatures. So this is after 1300 degrees C and 1200 degrees C and etc. We are still trying to understand why this is happening, but in the same time, we did the operando generation of nanomaterials in this material as well, and in the same way as we did for the nickel iron composition. We can see that from the electrochemical characterizations, indeed after switching at 2 volt and 2.2 volt, we also have the increasing of resulting current density, and the cell performance has been improved greatly as well. But by looking at the microstructure, we now have a very uniform distribution of nanoparticles across the whole area of the electrode, and the nanoparticles are primarily around 20 to 30 nanometers. Compared to the previous composition, we can see that the resulting current density is lower, and also the performance, the impedance resistance are much bigger in this composition. This is mainly due to the low conductivity as a result of a high doping at the B side. So the ongoing work is to looking at co-doping on the B side to improve the conductivity of this material, and then to further look at the exhalation phenomenon from the co-doped material. So this is just to summarize what we've seen that has affected efficiency of electrochemical reduction. So we can see that there are a number of factors we can play with to further improve performance and exhalation phenomena, but also we will try to understand the material properties more to linking to their performance, and especially using some in situ techniques to understand the exhalation behavior. And so sorry for the slow reaction. I think my Wi-Fi probably is just not really well behaving. So I think that's really me. We still have a lot of work to do to understand this method for operando generation of nanomaterials. So hopefully we'll be able to show more results in the future. And thank you very much for your attention, and also for the invitation to have me here. So I will be very happy to take any questions if you have. Thank you again.
Thank you very much indeed. Yeah, hopefully we can avoid echoes. But perhaps if you just have this microphone on when you're speaking. Thanks very much. I don't want to hear myself twice. Once is bad enough. Xiangling, could you show your face as well, please, if that's okay? Excuse my pronunciation, I'm rubbish.
I'm here, John.
Okay, if we could see your face, that'd be great. It'll keep my masters happy.
I'm here.
Okay. Okay. So we have a number of questions. Okay. So there's one just come in, which looks a good one to finish with, actually. So can I start with a general question for everybody? We've got 15 minutes, so we're on schedule. So we had a general question from Shimel Yerushalmi. And that is, if you think the future of hydrogen can become a good alternative to carbon and to carbon emissions. Does anybody want to take that? Paul?
Well, I can jump in on that one, John. I think that probably it's a resounding yes that it can be a good alternative. I think Sue in her one of her very first slides in the introduction captured some of the opportunities there, and clearly it has to work as part of just one piece of the jigsaw for the wider energy infrastructure. But I think the scalability and flexibility of hydrogen to contribute to such a broad range of decarbonisation is very compelling. And so I think the short answer to Shmuel's question is, can hydrogen become a good alternative? I would say a resounding yes, and I think increasingly we're seeing that being realised, not just through demonstrators, but actually in operation. So it's, I think, a big thumbs up from me.
I think there's no choice. It has to. Okay. Okay, from Callum, I think this is for both Xiangling and Paul. What are the next steps on the road to applications after creating a detailed model? How does this contribute to improving the fuel cell? So Chong, shall I ask you first? You speak first, please.
Yeah, well, as I showed, we just used the example to show that modeling can help us design whether we need a macroprocess layer or not. And we showed that adding a macroprocess layer in that PEM fuel cell cathode benefits the performance. And so the modeling can try to simulate a lot of design electrode architecture that probably do not exist yet. So that will then help us to design or come up with an optimal electrode architecture for giving better performance for fuel cells and electrolyzer. That's one side. On the other side, we can also use the model to help understand the phenomenon happening in the very complex 3D macrostructure, because some of the phenomena cannot be probed or very difficult to probe. Maybe Paul can correct me using the existing experimental techniques. So the benefit of modeling is we can use it to help us understand the fundamental phenomenon there, then taking there to design better electrode.
Okay. Before Paul step in, technical question for you. Can you say which modeling programs that you use for your research? It's from Eleanor Bakshender.
For me?
Yeah, for you. Which modeling? Yes, definitely for you. Which modeling program?
I think maybe the whoever asking the question missed it. It's a in-house code we developed at University of Surrey using lattice Boltzmann method. So it's a good method that is well suited for modeling liquid gas two-phase flow. So we have developed this 3D pole-scale lattice Boltzmann model that is able to simulate gas-liquid two-phase flow at the same time coupling with electrochemical reactions.
So it'd be okay if Eleanor contacted you?
Yeah, sure.
Okay, Paul, on the broader question, what comes next after the model to deliver application?
Yeah, sure thing. So, I mean, I think I will echo a lot of what Chong's already said. I mean, there are a range of sophisticated processing routes to make different design and microstructures. And there's an experimental route to making those microstructures, and there's a computational route to making those microstructures. And I think reconciling the two is very important. For the example that I showed in the microtubular solid oxide fuel cells, we've seen some really nice examples from the SuperGen programs, for example, Kang Lee's work, and Ian Metcalf's work on how you can design different architectural geometries for microtubular fuel cells. Obviously, some of the work that Dragos and Xiangling and your own work, John, has showed us how we can design, skeleton structures with exolved catalysts. There are a really broad range of quite sophisticated processing routes to making these microstructures. I think that by reconciling those microstructures with appropriate models, we can not only explore the fundamentals of how and why they work, but we can also, and I think this is what Chong sort of articulated earlier on, we can also think about how to optimize them. So in a sort of virtuous circle between the synthetic and materials chemistry all the way through to the device design, I think the modeling tools make a contribution to a more rapid and accelerated optimization. And that's what we tried to do, for example, with those examples that I showed about the microtubular solid oxide fuel cells. There are such a broad range of parameters that you can optimize. The model tells us which ones are the most successful routes, which dials you need to turn when you're making your fuel cell to get the best possible answer. Briefly, in respect to the software that we use, we do a lot of image-based modelling. So we first of all need to create a mesh from the tomography image. We use some software called Simpleware to do that. Once we've got that mesh, it goes into various different bits of software. Primarily for us, that's Star CCM Plus for computational fluid dynamics and Console for finite element modelling. And then one thing that, again, Chong has touched upon that we're able to do in the modelling packages, which is very, very difficult to do experimentally, is to isolate some really nanoscale phenomena. And in respect of the nanoscale diffusion phenomena within the gas phase, where we're looking at Knudsen type diffusion, we use some DSMC type approaches using a software package called Sparta. And actually, I think a real challenge to answer Callum's questions about what are the next steps for the modelling side of things, I think being able to reconcile continuum and non-continuum behaviour is a real challenge, and we're only just really starting to be able to do that as the resolution of our imaging techniques and the computational expense of the simulations becomes more achievable.
Okay, and just one final question for you guys. Paul, what's the pore sizes that you were able to resolve in your 3D visualizations? This is from Tim May.
Good question. It depends a lot on what instrument you use, but we would sort of comfortably get to sub 50 nanometer at some synchrotron facilities using techniques like Bragg coherent diffraction imaging. You can get to potentially sort of sub 20 nanometer in terms of the spatial resolution. Of course, when we look at coherent diffraction imaging techniques, the strain resolution that we get is much, much higher. So we can get picometer strain resolution and sort of tens of nanometers in terms of the imaged spatial resolution.
Okay. I'll move across the second half, by the way. I didn't mean finish the questions. I thought I'd move on.
Sorry.
Marina, don't worry. Dragos, question for you from Min. What do you think about the possibility of exsolving atomic clusters rather than nanoparticles? And would that be more attractive for catalysis or indeed low temperature electrochemistry?
Yes, the short answer is yes. This is definitely something that is possible and we're looking into. And actually the TEM experiments that I showed really helped us understand how to control that and how to get to that point, you see, because in exsolution it's relatively easy to control the size and let's say dispersion of the nanoparticles just by controlling the duration of the reduction process and the temperature of the reduction process. So you really have the tools to extrapolate the cluster size down to atomic scale should you want, but you have some limiting factors in terms of the diffusion of the atoms, which would control, you know, how much metal you can exsolve on the surface. So that's definitely something very exciting and very exciting application of exsolution, especially because this would result in this kind of socketed cluster. So we would be able to stabilize the clusters at the same time.
Yeah, and perhaps just to add to that, a question about is exsolution just for solid oxide cells, or can it be applied to low temperature fuel cells and electrolyzers?
I think definitely. Again, I think we need to play a bit more with the chemistry and ionics of the materials to be able to enable easier diffusion of ions. You know, to be able to trigger this at a bit lower temperatures. But clearly, we've seen that, you know, through electrochemical polling, the switching, we can actually change, you know, or go into, let's say, the thermodynamics that would favor exsolution at lower temperatures. So that would be a way.
Okay, and Xiangling, I was going to ask you, why did you pick on iron nickel as a coax solution?
So
why the iron in particular?
So okay. So from previous studies, we from the impregnation techniques, we saw that the alloy nanoparticles having like having synergistic properties compared to the single metals. So that's why we're thinking like maybe when we introduce alloy nanoparticles, we probably will have a better performance as well as like higher coking resistance. But it's through our study, we noticed that it's not only the nanoparticles are contributing the better performance, but also the bulk perovskite. Because when we introduce iron into the B site and together with the nickel, we see like the materials conductivity also greatly improved, and through like TG and XPS analysis, we see that. Then nickel iron co-doping has resulted in higher reduction in titanium 4+ and also more oxygen vacancies formation. So I think that's the performance is from not only the nanoparticles but also from the bulk perovskite. So we are also quite interested in other alloy nanoparticles, see how they compare with the solely nickel doped material.
Okay, then the final question, which I'll put to Xiangling first and then I'll pass to everybody else, is do you think it's possible to move towards earth abundant elements in the electrolytes and electrodes? So to reduce the amount of rare earths and noble metals on these components. But Xiangling, we start with you and then.
Yeah, I think that's definitely something we want to do in the future. And from my PhD work, I've seen that with different metals doping, different metal impregnation, like different nanoparticles introduction, we see great performance improvement. But I think that can be also transferred to exhalution phenomenon. So indeed, from the literature, we have seen a lot of exhalution, a lot of studies on looking at these cheap transitional metals as nanocatalysts. So that's really something we wanted to look at, and we are really at the moment focusing on these more achievable and more available metals as nanocatalyst.
Yeah, it's really important that we look at the whole system being net zero, not just electrochemistry or transport. Dragos,
Yeah.
so yep. Say anything?
Yeah, just to add something. So building on what Xiangling said, we've seen with exhalution that we can restructure non-noble metals to actually reach noble metal-like activity. So we already have in certain ways a method to basically reach that kind of activity. But I think that the base story here is the fact that structure is just as important and perhaps more important than chemistry. If you think about allotropes, graphite, graphene, diamond are the same chemical in essence, but the structure is what gives them function. And in the same way, in search for noble metal-like activity, we need to look at the structure in equal measure to the chemistry. So new methods of restructuring, nanostructuring, and controlling the structure of materials are just as important.
Paul or Chung, do you want to add anything to that before we close?
Yeah, I absolutely agree with what Dragos said just now. It's also a direction we'd like to develop a non-precious metal catalyst for ion exchange membrane fuel cells and electrolyzers. And it's possible there has been a lot of effort, for example, nickel molybdenum disulfide, nickel molybdenum alloys, although probably the stability still need to be improved. But as Dragos said, by manipulating the nanostructure and probably adding all the elements to stabilize, there's a big scope, especially as I showed the single atom catalyst, which showed much better performance than the bulk metal alloy. So there's a promising direction here we could keep working on.
There's one more question, but I think we'll stop there and give people 15 minutes to have a break.